I misled you a little bit about saying that size is complex. It is, it is, but it's a very, very early time manifestation of complexity. So early, and complexity really has its teeth when you're talking about long times. So the question is, can you say anything about very long times? This picture is from Daniel's talk, Daniel Harlow, but also Daniel Jaffer's this paper. And it argues, correctly I'm sure, that the quantum degree of freedom describing the SYK system is just the length between the boundaries. Length between the boundaries, from what I told you, can be translated into complexity, but there's also a Hamiltonian governing it. There's the Hamiltonian, p squared plus e, 2, I don't remember where the 2 comes from, e to the minus L, the distance. This actually is describing the gravitational interaction between the two boundaries. It happens to be repulsive. It's a funny thing, these boundaries tend to repel rather than attract gravitationally, but it is gravitational interaction. And it's governed by a Hamiltonian with a force, e to the minus L. Okay, here was my own picture. Before, while I was preparing my talk, I saw Daniel's talk and I screenshot it. This was my picture. It's basically the same picture, with the exception of the factor of 2 in front of e to the minus L. Incidentally, all of this wisdom is largely due from this point on to Henry Lynn. When I read the paper of the two Daniels, I found something very complicated at this point for the force law. Was that a mistake? It was a mistake, yeah. Henry calculated it, and it's just e to the minus L. It's kind of repulsion between the two of them. It likes to favor large separation. And that is, it's a manifestation of the Schwarzian action. What I wanted to say about it, yeah, well, of course, what it means is that the system, the length, the fictitious particle describing the length, comes in and bounces. And it bounces before it gets to the origin. The bounce is, of course, just the bounce here in the complexity or the length going from the bottom of the diagram to the top of the diagram. And notice that the length doesn't go to 0 in the middle. It reaches some minimum and it goes back out. If you think about this process in terms of the complexity geometry, now if you're not familiar with complexity geometry, this might not mean too much, the rest of what I'm going to say, but the picture that I had thought would make sense for this bounce, was a symmetric picture starting at the origin, starting at the identity operator, that corresponds to the thermal field double state, the identity operator. Going up means moving away from the identity operator. Moving down, you're coming into the identity operator, and certainly you see a bounce in this picture. This picture is purely a version of Nielsen's complexity geometry, very, very simplified. This is the picture you would get. But it's not the right picture. The right picture is this bounce, which never gets to the origin. The question is, where did the potential term, this e to the minus L, come from? If you are thinking about complexity geometry and thinking that the complexity is the action of this particle, this fictitious particle moving on the complexity geometry, there is no potential energy. The complexity geometry picture is pure kinetic energy. So where did this potential term come from? Well, I wasn't even smart enough to ask the question, let alone answer it. Henry was smart enough for both of them. And here is what he realized. If you look at time t equals 0, you see that the complexity never goes quite to 0 at time t equals 0. So that means that on this complexity diagram here, the phase point, or the point at time t equals 0, is not right at the center. The center is the identity operator. You'll have some complexity. Incidentally, that complexity depends on the temperature. The lower the temperature, the more complexity you have. And so that's the starting point, not the point at the origin. Now, what direction? By what direction, I don't mean what direction do you orient the diagram. That doesn't matter. What direction do you put the velocity of the fictitious point at this point, and what determines it? Well, the thing that determines it, go back a step, is the time symmetry of this. The complexity going up in time and going down in time is time symmetric. And the only way to orient the geodesic through that point, which is time symmetric, is to have the trajectory be perpendicular to the separation. Okay, so the fictitious particle moves like so on the complexity geometry. And this means that the fictitious particle has some angular momentum. Impact parameter, angular momentum, and therefore, guess what? Centrifugal force. That centrifugal force is exactly described by this e to the minus L perturbation, or this e to the minus L force. And so, in fact, the full action of this fictitious particle is kinetic energy. This kinetic energy, the e to the minus L, being the kinetic energy of rotation about the origin. There's more. I think I'll stop at that point there. As I said, the main lesson that I want to draw from this is that gravity, in both cases, is a complexity. There's no doubt about it in the second case, where the growth of the wormhole. There, it has nothing whatever to do with entropy. It has to do with complexity. I don't think it's an entropic force. And the evolution of complexity is a dynamical process governed by an action principle. That is something somewhat surprising. It surprised me. And that's where we are now. I like this subject because, well, I think it's a very beautiful subject. I think it's a very beautiful subject, the way that gravitation in various contexts is driven by the second law of complexity. I think it is worth your attention, and I think it is worth further exploration, much further exploration, many, many questions to answer. But I've taken up enough of your time. Thank you.
Okay, we do have time for a few more questions. Yes.
So for those of us who also like entanglement, is
I
that
like entanglement. I love it.
is that in there somewhere?
Oh,
Also,
I'm sure it is. Well, look, the reason that there's so much room for complexity to grow is because there are so many entangled states. So without entanglement, for sure, none of this would fly. I say in a sense, what entanglement is about the nature of a state. What complexity seems to be about is also about the nature of a state, but it seems to come in more when asking questions about evolution of states. So entanglement is an aspect of statics, in a sense. By statics, I don't mean things are static. I mean instantaneous states. Whereas it looks to me like much of gravitational dynamics is driven by this growth of complexity. Now, the growth of horizons, which also has its gravitational aspect and can be written in terms of Einstein's equations, happens to be an entropic phenomenon. Whereas the growth of the interior of the geometry seems to be a complexity phenomena. And the Newtonian force is sort of somewhere in between. It's a scrambling phenomenon. It's the short time version of complexity, but it's also got to do with something like thermal equilibrium. Yes,
I just find it a little confusing where the boundaries are. So the length is infinite if I go all the way to the boundary. So there's some thing serving as the boundary. Could you say something about that? Yes, it's the top
of the potential barrier. It's the top of the...
So that's an intrinsically defined place in the geometry?
I think if we make the approximation of spherical symmetry, can we do that?
Yeah.
Yeah, then a particle in the throat or outside the throat experiences a centrifugal barrier that has a bump in it. It's a thing which for Schwarzschild black holes happens at 3M. That's a high. Now, in the near extremal black hole, that potential barrier is very high. So a thermal particle experiences an enormously high potential barrier. If near extremal, the thermal particle has very low energy. So the thermal particle almost certainly gets bounced back. Even the S wave gets almost certainly bounced back into the black hole. And in that sense, there's a kind of dynamical isolation of the interior and the exterior. And that's where I would be inclined to put the boundary. That would seem to me the best place to define a boundary and to try to represent the boundary in terms of a York, Gibbons, Hawking term.
So from the complexity perspective, can you think about how to distinguish an approximately local gravitational theory versus a very non-local one where, for example, string effects could be large? Is there some condition, like a holographic condition that we can put?
I don't have a simple answer to that, but I think this raises the question about sub-ADS locality. Okay, so SYK and this story is not sub-ADS local. It is sub-ADS non-local. However, there's this long throat, which is many, many, many ADS radii, and so there's an element of locality in that long throat. So we get to have a local story, even though we haven't really mastered the sub-ADS locality. Does that in this context? One of the really big questions in my mind is how do you generalize this to higher dimensions, and how do we make sense out of sub-ADS locality, which I don't know the answer to.